Okay, so we will first start with the kinetic molecular theory of gases, then we will look at the pressure, then conversions, and then all these different laws. Then, the reaction stoichiometry and the collection of gases, and some of these other formulas also. Formulas that relate to the density and the formulas that relate to finding the molar masses of the gases, like unknown gas. And then formulas that relate to the, what is it called, the chi value, or the molar, like, what is it called, the molar, like concentration, or the molar amount. Okay, so we will discuss that. Like, I don't think so everything will be covered today, but let's get started first of all with the kinetic molecular theory of gases, which although is given in the back of the chapter, but I like to do it earlier so that you can, you can understand the behavior of gases, what it is. So KMT is basically a mixture, like, of the knowledge that we know about gases, the basic knowledge, and the theory basically. Now, what do you know about matter, first of all? Yes, somebody said it here. What is matter? Yeah. How do you define matter? Or what are the three states of matter?
Solid or liquid.
Very good. So there is solid, and then there is liquid, and we know that gases are a part of matter. Okay, so as you said, so gases are a part of matter. So if anything that has mass and occupy space is matter, right? Matter is anything, whether it's a solid, whether it's a liquid, or it's a gas, which has mass. It has mass and it's occupying space, means it has a volume. So that is, these are the two things. So whether it's a solid, liquid, or gas, even though you don't see the gases, but still those gases will have the certain weight, will have a certain volume. Okay, next is the solid. How are the particles arranged in solid? How are particles arranged in solid? Say that again. Condensed. So they are arranged in a very definite order. So they are very close to each other and they're very definite. So in other words, solids have a definite shape, right? Because the particles are very close and are very arranged in a very definite order. So they will have a definite shape and they will have a very definite, they will have a definite volume. The volume is basically what? The amount of space a substance occupies. That is volume. Okay. Besides that, in the solids, the attraction in the particles is very strong. Attraction in particles is very strong. So basically, I'm not going to write particles, you understand, they're all made up of particles. So attraction is very high. Okay. But the kinetic energy, that is the motion of the particles, is extremely low. So in other words, they're just vibrating. They're not moving. They're not mobile, but they're just vibrating internally. You don't see it. This is a solid, right? This is a solid. This pencil is a solid, but internally the particles are still vibrating. So we see that the kinetic energy is very low in the solids. Liquids, also the particles are present, but these particles are in a like in a mobile phase. So in other words, they're arranged in some random order. Okay, some random order. And so that because of the randomness, they do not have any definite shape. They do not have definite shape. So in other words, what do? They take the shape of the container, right? They take the shape of container. You put them in a bottle, they'll take the shape of a bottle. You put them in a glass, in a tumbler, in a container, in a box, wherever you put them, they will take the shape of that container. Okay. Now comes they do not have a definite shape. But the thing is that they still have a definite volume. Definite volume means they will occupy a very specific amount of space. Sorry. they will occupy a very specific amount of shape of the container, but the space inside that container also is very definite. So they have a volume is definite. Okay. The attraction in the particles is comparatively lower. So attraction is weaker, because of which they are mobile. They are mobile, they move. Okay, they flow, right? So there is a flow in the liquids. That's why I call it liquid. Next is the kinetic energy. The particles have kinetic energy. Okay, and that some kinetic energy is there, which is allowing them to flow. Okay, so that's the deal with the liquid. Now comes the gas particles. In gas particles, the gas particles are very, very far away from each other, very far. The distance between the particles is very large. So here they are not arranged. They are not arranged in any definite pattern. So the distance between the particles is very large. Distance between particles is very large. Okay. So when it's very large, then what happens? Attraction is minimal. There's no attraction. Attraction in the particle is zero. Okay. No attraction is present. Okay. So my spellings. So let's just go here. No attraction. ATTRACTION. Okay. Next is they also take the shape of the container. Okay, they take the shape of the container, which means that they are also mobile. They also are mobile. And this also means that the kinetic energy is extremely high. The kinetic energy in these particles, in the gas particles, is extremely high. Okay, so that's the thing with the gas particles. So no definite shape, do not have any shape of their own. Now comes the volume. Here's the thing with the gas particles. The volume in the gas particles, volume is actually the amount of space occupied by particles. Okay, but if the space is so large, the distance between the particles is very large. So that's the problem, that it is going to occupy like a large amount of space, right? But they can also occupy like a minimum space also. The reason is that the gas particles can be compressed. Gas particles can expand, gas particles can compress. So both the things can happen. So it's volume of the gases, volume of gases is indefinite. Indefinite. Why is it indefinite? Because gases can expand. Gases can expand. Gases can expand, and gases can be compressed. Gases can be compressed. So that's why their volume is not certain. Okay, volume is indefinite. Gases love freedom. That's another thing with the gases. Gases love freedom, right? No, the moment you, even if you compress them, after some time, they will find a small hole and they like to escape. So gases love freedom, and gases hate being compressed, hate being compressed. So that is why, the moment they find a little leak, they escape. Compressed, not compression. Hate compression. That's what I meant to say. Hate compression. Okay. So this is one thing. Now let's just look at back to this place here. Now, we know that you can take a solid and you can convert it into a liquid. You can take a liquid, you can convert it into a gas. You can take a gas and you can convert it into a solid. You can take a liquid, you can convert it into a solid. You can take a gas, and you can convert it into a liquid. And you can take a solid and you can convert it into a gas. Now, what are these processes called? Let's look at that first. Okay, first of all, liquid to gas, what is it called? Taking a liquid and converting into a gas. What is that process called? What is that phenomena called?
Evaporation.
Evaporation, very good. So basically boiling or evaporation at a certain temperature. So anytime the temperature of the liquid increases, it can lead to the vapors, vaporization basically. So this is vaporization, formation of vapors that convert the liquid to gas. Okay, gas to solid. Gas to solid. Yeah. Gas, conversion of gas to solid. And it's not condensation, but it is called solidification. 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 Now this happens when the temperature is very low. When it's very cold outside, right? And your windows are a little bit hot, the glass windows are a little bit hot. So what happens is that the air that is outside is extremely cold. When it touches the little bit warmer windows, the pane of the window panes, immediately the water vapors, they condense, but they solidify. Condensation is when the gas converts to liquid. When the gas converts to liquid, that is condensation. When you see when you see like a warm tumbler or a cup or a container or a glass or even a bottle, it's extremely cold, right? It's extremely cold inside. Outside air, when it touches the surface of this glass, you will see little water droplets. So the water vapor outside, which you couldn't see, the moment it touches the cold surface, it turns from a gas to a liquid state, and that is condensation. So that happens when the temperature is lower. Okay, but if it depends, if the temperature is extremely lowered, like a very, very low, like nearly 0 degrees Celsius, then it will solidify to a like an ice. It becomes ice. So icicles are formed in cold weather. Okay, next is solid to a liquid. Melting, very good. And so when something is melting, again, you have to increase the temperature. To melt, you take butter, you increase the temperature and it melts, right? Okay, next is from a liquid to a solid state. Liquid to solid. Freezing, very good. And so when you freeze, you lower the temperature. So freezing is lower temperature. Okay, next is from a solid to a gas. Solid to a gas. What is that called? Excellent. Thank you, Kenji. Sublimation. Sublimation. So sublimation directly converts a solid to a gas, and that happens when the temperature is temperature is increased. Okay, so here's a very interesting thing. The 3 states of matter, fine, 3 states of matter, solid, liquid, and gas. All we are doing is changing the way the particles are arranged. Here the particles are arranged in a very definite order. Here the particles are loose, but still close together. But here the particles are very, very far away. Okay, so these particles that are very far away, obviously, it's a gaseous state. Now, next thing is, we are not changing the identity. We are just changing the placement of the particles. So the actual identity of the molecule still remains the same, the chemical identity. Okay. Now, next thing you must have noticed is just what we are doing is changing the temperature. Here the temperature is going down. Here the temperature is increasing. One side is freezing, the other is melting. But that's the only thing that is bringing in solid to a liquid, liquid to a solid. Change in temperature Here, one place you give heat, give away the heat, and in the other one, you take in the heat. Same is the case here. Evaporation and condensation are opposite. So increase the temperature, evaporation, decrease the temperature, condensation. Same story here, solidification and sublimation. Increase in temperature is sublimation, decrease in temperature is solidification. So that's just basically the temperature change, right? Simple temperature change can bring that transformation. So this is one thing we know. Next thing, now when we are just looking at these gases, we look at them as like, of course, we are just focusing on the gases, and we find that the volume of the gas, we cannot be sure. We can be sure of the volume of a liquid. Here, mostly the volumes are measured in milliliters or liters, as you've seen in the lab, right? But the solids, of course, you can take the weight and you can measure them by, by the displacement method or by, other methods measuring. So you can get the volume, the amount of space. But gases, the volume is hard to find. But anyways, we still have to do something. So we'll say, okay, if you put the gas in a syringe, then it's going to occupy that much volume. If you take the gas and you put it in a cylinder, whatever the volume of the cylinder is, the gas is going to take that volume. So it's fluctuates, but the volume is still there. Okay. So because of that, the volumes, it's an indefinite volume for the gases, because by nature, they love freedom. They love to expand, and then they hate being compressed. So now let's look at this compression situation. Now let us look at what is pressure then. What is pressure? How do you define pressure? So here is a story that, let us say you are having a party, and here is the balloon you purchased, and in the balloon there are gas particles. Obviously, the gas is there in the balloons, and while you are having a party, what's happening? These gas particles, they hate being compressed. Obviously, you compress them in a balloon, right? So what they're doing, they're hitting the walls of the container. They are hitting the walls of the container, and when they hit, but then they bounce off. Okay, so they hit and they touch. And why are they doing it? Because they're looking for an outlet. So the force with which the gas particles strike the inner surface of the container, that force is called pressure. Inner surface of the container, that force is called pressure. Okay, so every particles is hitting the walls of the container, and that force is equal to, so pressure is equal to force per unit area. So pressure is equal to force per unit area. So every particle is hitting the container like at a certain spot, and that little spot here, so all these different spots, it hits all those different spots. Those spots, that's the force with which that it's hitting, that is called the pressure. Okay, now besides that, these gas particles are not just hitting it. What they are doing, that they are bouncing off. So these are also, these particles, once they hit the container, they bounce on the walls of the container, they bounce off. Okay, so these bouncing off, they bounce off and then they come back and then they hit the container. So this is continuously going. So bouncing off and then hitting the walls of the container, bouncing off back. So this is called collisions. So basically they are colliding against the walls of the container. Okay, hitting the walls, and then these walls. So this is also called, this term, the scientific term is colliding, or it's also called collisions. So while they are doing that, they are also going to collide with each other. Okay, collisions are also with each other. And what type are these collisions? These collisions are elastic collisions. Elastic collisions are like that of a rubber band. You take a rubber band and boom, it strikes back. So that is elastic collisions. So elastic collisions are present in these gases. Okay, these collisions are elastic, means they just hit gently. So they don't like hit that it breaks or it cracks the wall. No, they just hit and then bounce off, hit, bounce off, hit, bounce off. That's how it goes. So elastic collisions are more like a rubber band. So keep that in mind. Yeah. Say that again. Oh, this is pressure. Pressure is equal to force over area. Okay, got it? So then we will look at the units for the pressure also, but for now, just keep that. So it's a rubber band. Okay, rubber band, like a rubber band, elastic collisions. They're hitting each other also. Means that, okay, it depends. See, chemical reactions occur when the molecules also hit each other. In that case, when they're hitting each other, the bonds break. In this type of collisions, that's why the term elastic collisions is the bonds are not breaking, you know, just like a rubber band strikes and it bounces back. So it's like that type of collision. So it can bring a little impact, but it doesn't bring the chemical change. That's what it is. Okay. Now, another thing with these is that when they are hitting, then they effuse and diffuse too. Eventually, these gas particles, they are able to find a route and they escape because their goal is, you know, freedom. They want to expand. So the gas particles escape after some time. Okay, after some time. And you've seen a balloon that's nice and hard from the surface. After like next morning, it's very soft, like a very soft. It has a very soft, you know, very plumb kind of a, you know, feel to it. So what's the deal? The gas that was inside the balloon has escaped. So this escape also has been measured. So that escape is called effusion. And it's also called diffusion. So both the terms apply, effusion and diffusion. D-I-F-F-U-S-I-O-N. Okay, so what is effusion and diffusion? Diffusion is basically that escape means what? Escape, eventually they are going to spread out, like spread over all this spread. So diffusion is a simple spreading of gas particles. Okay, just spreading. This is normal, just a general term. But effusion, you measure that spread with a speed. What is the speed of the gas particles? Which one is spreading faster? Okay, so the speed of particles, you know, that are spreading. Okay, that are spreading. So that has been measured, and we will study about this more. So just so you know that effusion has been, you know, we have verified this. There's a formula actually for that. And that is speed which you can measure. But diffusion is a general term. Like though the gases are diffusing, means like they are moving from, you know, from a higher concentration to a low concentration, basically. Okay. Next is, we also see this rate of effusion. What does it depend on? This is depend on the mass of the gas particles. Mass of gas particles. And this mass, because the gas particles are so small, so we measure this mass in kilograms. Okay, but mass means the weight, and that also applies to the molar mass of the gas particles. So a common sense, heavier gas particles are going to move slowly, lighter gas particles are going to move fast. Okay, so the molar mass of the gas plays a role in their like in their spread, okay, in their expansion. So heavier, gas particles move slowly, and vice versa for the lighter ones. Okay, the vice versa means like opposite. So the lighter gas particles are going to move fast. So these are the basic things. Now let me ask you some questions. Let's just do some. Oh, there's something else also. We can just cover it here. That when the temperature, the effect of temperature is when you increase, the effect of temperature means as the temperature increases, the kinetic energy of the gas particles increase. Kinetic energy is what? The kinetic energy is the motion with which these gas particles are moving. They are basically colliding against each other and the walls of the container. So they're all the time moving. So as you increase the temperature, the movement of the gas particles increase. So motion of particles increases. Okay. So temperature effect on gases, and that is when you increase the temperature, kinetic energy increases, motion increases, and what else increases? Pressure increases. Now they are going to hit the walls of the container with a greater force. You see that? As you increase the temperature, you see that the kinetic energy increases. The force with which they are striking the walls of the container eventually increase. So that's the relationship between the temperature and pressure. Now I'm going to ask you a few questions. How were gases discovered? How were gases discovered? Just a presence of gas. How was the presence of gas discovered actually? Yes? Okay, let's see. Yes, guys? How was the presence of gas discovered in nature? From heat? How from heat? Fire? How? How from heat and fire? How? Explain a little bit more. Explain a little bit more. Smoke rising from fire, heating, burning something gives off a gas. Very good. So first is that we observe this in the reactions, chemical reactions. Okay, chemical reactions. So in the chemical reactions, we observed some fizzing sound. We saw some fumes. We also saw some bubbles. Okay, bubbling, fumes, fizzing, all these things was observed, that led us to believe that there is a third state of matter or something is being formed that is like not liquid, not solid. So that's one thing. Next is sometimes you can't see the gases, like the whole bunch of them. Oxygen. Can you see oxygen?
No.
But you're breathing, right? How do you believe oxygen exists? Yeah. Yes, Heath. How would you believe that the oxygen is existing? You can't see oxygen. Say that loudly. I can't hear now.
Oh, sorry. I was just saying, like, we'd be dead if. Yeah.
Okay. Say that again. Yes, so if you don't breathe in, obviously you're breathing in oxygen every time, right? You're breathing in oxygen, and you know it. If you just close your your mouth so you don't breathe, then you feel like, okay, you can survive, right? So lack of oxygen is going to create a very a very difficult situation. So we come to know that I'm we are existing on this earth is because of a certain component of the air, which is the oxygen. So we will discuss how was oxygen discovered. Here's the thing, and this thing experiment you will do at home also if you want to. It's a very interesting experiment. You take a trough. A trough is like a petri dish. Invert it as invert a glass over it. Okay, invert a glass, and in that glass, put like 5. So 1, 2, 3, 4, 5. Okay, so roughly 5. Okay, now inside put a candle. Inside this, put a candle, and outside put water. Put water outside. So here is the water. Okay, outside is the water. Now, what you're doing is, let me just get this a little bit here. Now, you burn the candle. First of all, note, like there's very little water, just water just covering the base right here. Right, just covering the base like here. So very little water, just covering the base. So now you light the candle. When you light the candle, what's going to happen? The candle will begin to burn, right? The candle burns. When the candle is burning, then it's fine. But after some time, we see that the level of water begins to rise. Level of water begins to rise up to like 1/5 of this level. So 1/5 is left. And that's the time when the candle goes off. The candle goes off when the level of water rises to 1/5. Now you can repeat this experiment, use a different container, a bigger container, a smaller container, so the size of the candle also bigger, smaller, whatever, the amount of water you want to add in the basic, this container, that is also fine. So once you can make some changes. No matter how many times you repeat this experiment, you will always find that the level of water rises to 1/5. Never half, never 3/4, never 1/4, but it's always 1/5. So 1/5, so that led us to believe that 1/5 of air, so inside is what? Inside is air. So, but it's only the 1/5 of air is oxygen, and that oxygen is the one that supports burning. Okay, after the oxygen is used up, then that's the end of it. Carbon dioxide is released. Carbon dioxide does not support burning. So what happens? The candle goes off. The candle douses off on its own. The candle douses off on its own. It won't work, right? And what happens is there's 1/5 of air that was in the container. Once it got used up, a vacuum is created. A vacuum is lack of something, lack of air, basically. So vacuum is created when 1/5 of air gets used up. Okay. Now, when the vacuum is created, vacuum is what? Emptiness. It is emptiness. And to fill that emptiness, what happens? The level of water rises. So level of water rises to fill the 1/5 of vacuum. And that led us to believe that what that is whole 1/5 of something that is present in the air is that supports burning, and that is oxygen. That led to the discovery of oxygen. Okay, so these are just some of the ways these gases were discovered. So this is one thing, discovery of oxygen, and then they did all find the identity of it. Next is, there is a concept, there's laughing gas, which produces the effect of laughter, right? So when I think it is nitrous oxide, N2O, if I'm not mistaken, but the effect is produced by this laughing gas is it makes you laugh. So there was this one professor, he's working on this. So what is happening? When this professor is working on a certain experiment, the laughing gas is produced. So when he's inside the lab, he laughs. When he comes out of the lab, he's fine. He goes inside the lab, he laughs. Comes outside, fine. So you see, it's not all the time about fizzing and fuming and bubbling. It's about the effects of the gas in the environment also. You know, sometimes it's the smell of a gas, sometimes it's the effect is in the case of, you know, here it is making you laugh. Then there are lacrimators also, which make you cry. Tears come out of your, you know, eyes. Sometimes gases have very peculiar smell, like a butane gas. You know, in the labs, we use butane in Bunsen burners. The gas that comes home, again, it's butane. So whenever it's leaking, you come to know that, oh my God, the gas is leaking, and it's very flammable gas. So those things. So gases, you know, they have made their presence felt. So one of them is a laughing gas. Inside the lab, laughter. Outside, no laughter. So his students said, okay, what's wrong with the professor? He keeps laughing. So they said, okay, let's figure out what he's working on in the lab. So they go inside the lab, they all start laughing. They come out of the lab, they're fine. They go back into the lab, again, the same story. So they're like, okay, let's see what is he working on? What kind of chemical reaction is that? And so they find that that was the nature of the gas that was produced, was to make people laugh. Although I'm telling you, it's a very toxic gas also. So it's not that laughter is like that happy laughter. It is going to affect the health. So don't play around with this gas anyways. But anyways, other gases were also discovered in the same way that, like, for example, you've done this experiment in the lab. Now you guys have to tell me, I'm just testing you whether you remember this or not. You worked with the gas in a lab. What is the name of that gas? And how did you identify it? This is your lab question. Yes? You worked with the gas in the lab. This gas in the lab, you generated it also. We had a lot of hydrogens. Excellent. Very good, Kenji. Okay. So how did you determine that that was a hydrogen gas? What did you do? Some of the students, I helped them in the beginning. You remember, for hydrogen, it's a very peculiar reaction. Forgotten? You guys remember? A gas that was in the lab, that you did something to it, popping noise. Very good. Very good, Akvi. Okay, so it makes a pop sound. How is this pop sound produced? Remember something in the lab? How is this pop sound produced? Fire. Very good. So when you bring a burning splinter, so that burning splinter is, the moment you bring it near, pop, that popping sound is produced for the hydrogen gas. So that's how, you know, we came to know. Next is, there are other gases also, like for example, carbon dioxide. You know, carbon dioxide, you're breathing out carbon dioxide. So when you put it, so here is this carbon dioxide, we are breathing out. Okay, so here's the thing. So if you have, let's say, calcium hydroxide, here is calcium hydroxide, calcium hydroxide. Okay, and this calcium hydroxide is in a container, right? And here you take, what is it called? A straw. You take a straw and you blow into it. Blow into a straw. What would happen? Blow into a straw. So what would happen? So here is this person, and you will see bubbles first of all, right? You're blowing into the straw and into the machine. Okay, so this is this one person and he's blowing into that. So this is calcium hydroxide, releasing carbon dioxide. We release carbon dioxide. So what is formed here? That we will see in this case, generally in the past, calcium carbonate is formed, and calcium carbonate is solid. Okay, so they would see like white colored, what is it called? Like rocks would settle down at the bottom. And that is the calcium hydroxide, calcium carbonate is rocky. So a reaction is produced actually in this case. So that's how we were able to determine, like, wait a minute, I'm producing some gas that can bring out this type of chemical change. So that's how the carbon dioxide was discovered. So anyways, all these, and you can just go on and on. But in nature, in general, how was the atmosphere discovered? Do you have any idea? Or how did we figure out the atmosphere? How did we know that there is atmosphere? Yeah, how did we discover the atmosphere? Atmosphere is what? Atmosphere is mixture of gases. But how was this atmosphere? We are actually living in the ocean of air. Ocean of air. We guys are living in the ocean of air. Okay, so this ocean of air is a mixture of different gases. 21% is oxygen, about 70 or 72% is nitrogen, and then the rest is other gases. So like other gases are the remaining, occupy the remaining. So carbon dioxide is like really small because it's getting recycled, right? Okay, so atmosphere, how was the atmosphere discovered? Any, this is not, these answers are not in your book, but it's a very like common. How? Yeah.
This is kind of like the first experiment that we showed.
Oh, yeah. Okay. Without doing any experiments, your daily life. How would you know that the air is around us? Daily life. Think about it. Think outside the box, guys. Don't just stick to. Say that again. I'm higher altitude. Okay, very good. So when you go up on the hills, you feel there is less air, right? Up on the hills, the air is thin, but on the beaches, the air is thick. So air is more. Okay, so that's one thing. And then up on the hills, what happens? You feel ringing in your ears, ringing in ears. So that is, you feel that pressure, air pressure. Besides that, okay, I'm going to just, you see the things, the air, the atmosphere in our daily life, we see the flags are fluttering. The flags flutter in air, right? How are they fluttering? The leaves, the dry leaves, they begin to like, whirl like a whirlwind. When it comes, it moves the leaves like in a circle, right? Like that, you must have seen. The leaves on the trees are also like they also flutter, or like the flags and the clothes. You hang the clothes outside, and these clothes are, on the on hangers or whatever, the clothes, your scarf in your neck, right? Your hair, they all move with the winds, right? Not only that, the masts of the ships, these masts of the ships, they bellow, and that's how the ships are moving. Okay, and then we also hear in our life experiences the storms, right? The storms come, the winds blow very fast someday, winds are blowing, the winds with a fast speed, the movement of the winds in general. So all that led us to believe that there is something much more than just solids and liquids. So that's how the gases got discovered. Now we are going to look at another piece, that is pressure. Let's look at pressure. Pressure. Now, there was this guy, Torricelli. He was only 16 years old. 16 years old. Okay. 16 years old boy, Torricelli. What he did was, his uncle, now this is at the time of Renaissance, and I don't want you to try it yourself, but this happened, at the time when we were still discovering science, learning things by trial and error. So here is, he took a trough, like a small dish, and in that he put okay, so here he put what is it called? The capillary tube. It's open on both the ends. This capillary tube is open and it's very thin. I made a thick one just to show you, it's a thick, very thick. So he put 1,000 markings on it. 1,000 markings. Very intelligent boy. But he made 1,000 markings on it. And from here, he bought, what is it called? A mercury, liquid mercury. So he got the liquid mercury from somewhere. And like I said, I don't want you guys to try that at home, because liquid mercury is like neurotoxic, and it can, obviously cause a lot of damage. It's very toxic. So he has this little apparatus here. This is an apparatus. So here you have mercury. This is the capillary tube, and then that's marked. Now he took this apparatus. He wanted to see what is going to happen. He took it on the plains, took it on the beaches, and took it on the hills. When it was at the plains, the level of mercury was 760, and this was all in millimeters. Okay, 760 at plains, millimeters. But when he took it on the beaches, the level of mercury, so on the plains, what happens is, this level of mercury, it rises up the capillary tube and reaches up to 760 millimeters. So that is all happening at plains. He continued to test it, all these plains, little bit variation here and there, but generally that range is 760. But when he took it on the beaches, he found the level of mercury rose higher than 760 millimeters. 760 millimeters higher on the beaches. But when he was, no, wait 1 second. One second. 7 beaches is a higher pressure. So it would be, what am I doing here? 760 millimeters is right plains. When on the beaches, the pressure is very high. So pressure is high. Yeah, it will be over 760, right? And then when it is on the hills, it is lower. So it's less than 760 millimeters. Okay. So what is this happening here? Outside, as we said, there is this atmospheric pressure, which is basically the weight of the air. The weight of the air over us. We don't feel that weight. It is a lot of weight. It is equal to like several thousand cars standing upon us. We would be crushed under this weight, but we don't, because the equal and opposite weight is being applied, so it's like all in several directions. If the same weight is coming from the top, the equal and opposite weight is going from the bottom, so overall it's being nullified. So our things are stable and stationary. If the weight is coming from this side of the air, the equal and opposite weight is coming from this side, so the things remain. This table is not moving. The book, is stationary. This pen is not rolling over, because the weight it's normalized. It's equal in all the directions. So overall weight is canceled out. However, the weight still exists. The pressure, still exists. And when this pressure falls on the surface of Mercury being liquid, begins to move up the capillary tube. So as it moves up the capillary tube, on the plains, the maximum it has reached is 760 millimeters. Beaches, because there's a more air on the beach. The air is already thick on the beaches, and the overall, because of the human activities and all, the air is thick. So that thick air pushes more pressure. So the level rises above 760. So the more the pressure from outside, the higher, more the pressure from outside, higher the Mercury moves. Okay. And on the other hand, on the hills, lower the pressure means, that there's nothing that is going to push the Mercury from outside with that much force, very little air. So a little bit of the Mercury moves, but it generally reaches up to 760, but it stays below 760. So lower the pressure, then the lesser the Mercury rises. Okay, in capillary tube. All right, so that led to the discovery of the way we take the measurements about pressure. So we understand pressure, but we are taking these measurements on the pressure, and we started giving some units to it. So he said, okay, one torr is equal to 1 torr will be 1 millimeters of mercury, or 760 millimeters of mercury is equal to 760 torr. So this is with respect to this Torricelli. Okay, next is this also means 1 millimeter of mercury is equal to 1 torr. Okay, now it also means, now we said, okay, what is this one? So we always like to use the standard unit. So the standard unit is 1 atmospheric pressure. So 1 atm is more of a standard. It's an STP value, standard. Okay, so that is equal to 760 millimeters of mercury, and 760 millimeters of mercury is equal to torr. Okay, so that's one piece. Next is there are others also. Inches and other ways. Okay, other ways. So 1 atm is equal to pound square. Air level at a sea level is 14.7. The way they have given in the table is so weird. So best is you write it down, what I'm showing you. 14.7 pound per square inch. Okay, PSI. This is another. So that's pounds per square inch. Okay, 1 atm is that. Now, besides that, 1 atm also means 101, 3 to 5 Pascal. 101,325 pascals. PA stands for Pascal. Okay. Then one kilopascal, 1 kPa. kPa is 1 kilopascal. 1 kilopascal is equal to 1000 pascals. Okay, 1000 pascals. And so write these down. And then we have 1 bar. They have given bar also. 1 bar is equal to 100,000 pascals. 100,000 pascals. All right. 100,000 millibar is 1 bar, or 1 bar is equal to 1000 millibars. So that's one thing. 1 inches of mercury, 1 inches of mercury is equal to 3386 pascals. 3386 pascals. So these are all the units. These are all the units of in which the pressure is measured. Okay. Now let's look at this. Some of these problems here. So as you know, for the pressures, we now have these barometers to measure the pressures. So the reading, let me write this down. Pressure readings are in barometers. Pressure readings. The name of that instrument is called barometer. BAROMETER. Okay. Convert the pressure. Okay, let's just do 1 or 2 here. Problems. This is page. Okay, now I have this green book. So page 460, and this is the example 9.1. Okay, let's do these conversions. Okay, here you are given 29.2 inches of mercury. Okay, so they're saying convert it into torr. Find how much torr is that. So you're going to look at it, the inches of mercury and torr. Inches of mercury and torr, is there a relationship between inches of mercury and inches of mercury and torr? So we know that one second, inches of mercury, where is that? There's no direct relationship. So we will have to do, yeah, right here. This is also 760 torr. 760 torr. Okay. Okay, so this is how what you'll do. You're going to first take the the inches of mercury and convert that to inches of mercury to Pascal. Oh, there has to be, okay, if we do it by Pascal, I just want to not go by this route. I want to do this thing. Inches of mercury to Pascal and Pascal to Pascal to ATM. ATM. This one. And then ATM to, and then we need to find a torr. Okay. ATM to torr. Okay. I'm not doing that the way the book is showing that to convert the inches to millimeters, which you can, but let's just do this. So 29.2 inches of mercury. First is convert that to Pascal, because we don't have a direct conversion of inches of mercury to torr. So we know that 1 inch of mercury is equal to 3,386 pascals. And then we get rid of this Pascal and make it into an ATM. So 101,325 pascals gives you 1 ATM. Okay, and then we know that 1 ATM is equal to 760 torr. Okay, so this way we are getting rid of inches of mercury, pascals and pascals, ATM and ATM, and you're just left with the unit of torr. So now you do 29.2 times 3,386 times 1 times 760. Huge number, but that's fine. 1 into 101,325 times 1. Okay, so what do you get here? Seven.
741.59.
Very good. 741.59. So your book is giving you 742 torr. Okay. So that's one piece I've done. The next is, let's look at the other one, millibar to inches of mercury to millibar. So this is one piece. This is A. And I'm going to do D, millibar, millibar. Find it in millibar when you are given 29.2 inches of mercury. Okay, so same thing, millibar. Now you look at here, you are given millibar and convert to inches of mercury. I think we'll just have to use the same thing. Take the inches of mercury, convert that to pascals, and then from pascals to right here, 1 bar is 100,000 pascals. So, and then convert that to millibar. So these ones, okay? So let's do this. 1 inches of mercury is 3,386 pascal. So 29.2 inches of mercury times 1 inch of mercury is equal to 3,386 pascals, 3,386 pascals. So because we need it in millibars, so we need to convert the pascals to bars first of all. So here we have 100,000 pascals is equal to 1 bar. 100,000 pascals is equal to 1 bar. And since the question is asking us in millibars, so we're going to convert 1 bar is equal to 1,000 millibar. Okay, 1 bar is 1,000 millibars. So here you see the inches of mercury cancel out, pascals and pascals cancel out, bar and bar cancel out. You're just left with the millibar. So now you do this math, 29.2 into 3,386 times 1 times 1,000 over 1 times 100,000 times 1. What do you get here?
0.989.
No, millibars. We need it in millibars. Yeah. 989 millibars. All right. Okay, guys? Uh-oh. How do I get there? How do I get back to my room? And I don't know if I do this. Oh, right there. Okay. All right. Next is 988.7. Very good. So 988.71. Very good. Millibars. And that's going to give you, then becomes 989 millibars. Okay, either way. So I highly recommend that you copy these. Copy these on your handout. Copy these units on the handout, because on the exams, you are allowed to use the handouts. Okay? Don't forget that. And you need this anyways for your test. So that's how we do this. Next is so what is this here? They are giving another question. Calculation of the barometric pressure. Okay. Show the calculation supporting the claim that atmospheric pressure near the sea level corresponds to the okay, you know what? I'm not going to give. This is like very, you can leave that. Okay, I'm going to just put this here. This is as far as you know how to do these conversions. We are not getting too detailed into. So leave 9.2 where they start getting into like converting, like how to get these hydrostatic pressure and all that. I mean, you can read it on your own, but you know, you don't, this is not something we do every day in our lives. So leave 9.2. Next is okay, same thing. The rest is just these pressures, conversions. The rest of the calculations are open-ended manometer, close-ended. These are just conversions. Okay, next is we are looking at the scenario with, so you can, yeah, leave 9.2, which is talking about the ways of getting the pressure. Okay, next is, we got these conversions. Next is, let's look at number one is, first of all, Boyle's law. I mean, your book is starting off with the ideal gas law, which is again, you know, doesn't make sense. Start with the Boyle's law, then start with the Charles law, then Avogadro's law, everything, all the laws done, then we come to the to these laws. But before we start that, I want you to get into this. Let me know, first of all, the names. So let's look at the real gases. There's a concept you're going to hit again and again, real gases versus the ideal gas. Ideal gas. So real gases are like, for example, the gases that you've seen, you know, noble gases. So what are the names of the noble gases? What are their names? Very good. So neon, helium also. Helium, yeah. Helium, neon, argon, krypton, xenon, and radon. Okay, so these gases are atomic gases. They are atomic gases. They are just made up of one type of particles, okay? Just one type of atoms, basically. Next is, when we talk about that, there is almost zero attraction in these particles. Zero attraction in particles for the noble gases. Okay, now let's look at the other type of gases called a diatomic gases. So which ones are those? Diatomic gases. Very good. Very good. So let's start. Hydrogen, nitrogen, oxygen, and fluorine, then chlorine, then bromine, then iodine. That's it. So these are molecular gases. Yes, they are made up of same type of particles, same type of atoms, same type of atoms, but they are, two of them of the same type, and two of same type of atoms. So there can be minimal attraction. Some attraction is possible because see, fluorine is highly electronegative, chlorine highly electronegative, bromine highly electronegative, so very electronegative gases, but there is a minimal attraction in these particles. Minimal attraction in particle. All right. Now let's look at some other type of gases. These are called the real gases. The real gases. Now you guys give me the names. Carbon-based gases. Very good. Carbon monoxide and very good. And the whole of organic chemistry is basically carbon-based. So we have methane, we have ethane, C2H6, we have propane, C3H8, we have butane, C4H10, and so forth. Okay, let's look at nitrogen-based gases. Yeah, nitrogen-based gases. NH3 actually, NH3. So let's do this here. Nitrogen, this is, remember we talked about, there's nitric oxide, there is nitrous oxide, then there is nitrogen dioxide, okay? And then we have nitrogen dioxide, and then we have, what is the other one? Ammonia, NH3. Okay? Sulfur-based gases. Yeah, sulfur-based gases. Sulfate is the anion. Sulfur dioxide, very good. Sulfur dioxide, sulfur trioxide, H2S, hydrogen sulfide, very common gas. All right. Then similarly, there is a phosphorus-based gases. Phosphorus-based gases are like phosphine, PH3. Okay. And then there are other gases also, many other types of gases also, but made of different atoms. Made of different atoms. So because they are made up of all these different atoms, and oxygen is there and so forth, so there is going to be attraction exists between these particles. So attraction exists between these particles. Okay, if there is attraction, now here's a very important piece. There is the last one is the ideal gas. Ideal gases are ideal gases. So what are the postulates of ideal gases? Ideal gases, number one, no attraction exists in between the particles. No attraction in between gas particles. Okay, that's one piece. We also believe that ideal gases follow all gas laws. Why do they follow all gas law? Because they do not undergo change of state. Change of state. Okay. And the last but not the least is that all motion stops, all motion stops at 0 degrees, at 0K, means the absolute zero, at 0 Kelvin. This is absolute zero. So we believe that all motion stops at absolute zero. So this, it means that for ideal gases, you can stop the motion. But here's the problem, that motion for any of these gases that you see, the real gases, these gases over here, the real gases, the diatomic gases, and the noble gases. So when they are cooled, when these gases are cooled, when these gases are cooled at absolute zero or near absolute zero, what is going to happen? Motion does not stop in the particles. Motion does not stop. But what happens? Do you guys know? Yeah. What happens at absolute zero? Yeah. Yes. Yes, guys. What happens at absolute zero? Say that again. All motion will stop, we assume, but for other gases, these gases that we talked about, the motion does not stop, but change of state occurs. Do you know what the name of that state is? You know what is the name of that state? Starts with B. Starts with B. Bose-Einstein condensate. This is the fifth state of matter. So the three states of matter already know, solid, liquid, gas. If you increase the temperature, they become plasma. But if you decrease the temperature, that is the absolute zero, then we will see Bose-Einstein condensate. Got it? Now, it is not possible to stop the motion of the particles because there is because you know the electrons, not possible. Electrons existing as waves, electrons existing as particles, electrons spinning on their axis, clockwise and anti-clockwise. Okay, so because of that, we have no control over here. We cannot make the electrons not become a wave, not become a particle, or stop spinning. Not possible. Even at the absolute zero, we have not been able to accomplish that. So even at the absolute zero, the electrons keep moving. And as far as the electrons are going to move, there is going to be attraction. That's the thing. So clockwise and anti-clockwise motion does not stop, even at atmosphere, even at absolute zero, and that applies to the real gases. So clockwise for all real diatomic and noble gases. So then what are ideal gases? Ideal, as the name says, ideal. Ideal is just, these are just mathematical only present mathematically. Mathematically, you can prove their presence, but that's it. In reality, they don't exist. So mathematically present, but not real. Real gases are like what we see, what we feel, what we experiment with, what we are generating. So the thing, what is the deal with them? Here's the thing, for the gas laws, the noble gases behave like ideal gases. So they are not the ideal gases, but they behave like ideal gases. Okay. Remember, we discussed here that the ideal gases do not undergo any change of state. So yeah, for a long time, these guys are going to stay. So they behave as ideal gases for long period of time. So as far as they are in the gaseous state, gas laws are going to apply. Okay. So next is the diatomic gases, because there's minimal attraction. So they are also going to behave as ideal gases, because whatever attraction they had for each other, that has been now sitting in the bond formation. So, so they behave as ideal gases for some time. And then after that, they undergo the change of phase. Real gases, yes, same thing. They obey or they behave like ideal gases for a short span of time. Behave like ideal gases for short span of time. For short span of time only. Okay. So yeah, after that they undergo change of phase. Why? Because due to electronegativity, oh, okay, due to electronegativity, these gases quickly convert to another phase, or can quickly undergo the phase change. Gases quickly undergo phase change. So whether they exist as solid or a liquid, it doesn't matter. The gas laws only applies to a matter in the gas state, which should look like this. Gas particles should be very far apart. No attraction in these particles. Kinetic energy should be very high. So in this case, if the phase change has happened, then the gas laws won't apply. Okay. So then the ideal gases are what? Ideal gases are, they exist only mathematically. We can only prove their presence mathematically. We say that, oh, you keep on increasing the temperature, the volume is going to continue to increase. It doesn't happen on this earth. Explosions happen and those things. So same thing, if you take a gas and you put in a lot of pressure, then, generally we've observed they take a phase change under extreme pressure. But ideal gases will not show any change of phase, no matter how much change you make in pressure, how much change you make in temperature, those things. So they will continue to obey all gas laws. But these gases, the real gases, the diatomic gases and the noble gases, these guys, they obey all gas laws only for a very short period of time, because they quickly undergo the phase change. So for the time period they are gases, only that time period they will obey as gas laws. Okay, they will obey the gas laws. So that's the basic thing. Any questions do you guys have so far? Okay, so I'm going to just stop here, because next time when you come, we will start with the Boyle's law and like other things. the Charles law and like combined gas law. Yeah, so we will finish off the remaining stuff. And if you guys have any questions, ask me, or you can just send me the questions, you know, non-ideal behavior, all this, we will look at, look into those things. Okay. All right. Okay, guys, I'm going to stop recording.